time, basically you just take this, just the mass of it, and you get 3.5% of it, which, you know, they have this, which is pretty hard to do without a calculator, so I turned the whatever 3.5% as 7 over 200, which I multiplied by that, and you know, I basically got something very similar to 35 because of the 3.5% aspect, but it's a little higher, so that's why they put 36. And then you just divide it by the gram formula mass of sodium chloride, and you get 0.62 moles. So that's that. This one, so again, because this person is drinking a large quantity of ocean water, which has a lot of salt in it, this means that the blood will have a greater amount of salt in it compared to the cells, which means that the blood is hypertonic in comparison to the cell. So we're going to cross out the ones that say hypotonic, and then we're left with B and D, which are both hypertonic. But what happens when your cell is in an environment that's hypertonic? Hypertonic means there's more salt and therefore less water. And your cells, in comparison, will have less salt and therefore more water. Water will, through diffusion or osmosis, water will leave the cell and go into the, you know, hypertonic environment, and that'll cause the cell to shrivel up. If it was the opposite, it'll cause the cell to burst. This one I just went through really fast, but the answer is pretty obvious. I mean, first of all, it's a colligative property that, you know, adding salt to water causes boiling point elevation. Other colligative properties are freezing point depression. I think vapor pressure should go down as well, and I forgot the other one. But yes, I don't know why I put whatever decrease. I went through this fast, but basically the boiling point is going to increase due to boiling point elevation, which is just a colligative property. And if that is the case, that means the temperature needs to be higher. By the way, boiling point, just basically when something boils, it means that the vapor pressure is equal to the atmospheric pressure. So they wrote external pressure. That's what basically is the same thing as the atmospheric pressure. And greater average kinetic energy is just another word for temperature. So basically, boiling point elevation means the boiling point increases, and which means that the temperature required to boil increases, so hence greater average kinetic energy. And boiling is when vapor pressure equals the atmospheric pressure, so yeah, that one's going to be A. So, okay, this one is just talking about why is ice less dense than water? For mostly all other substances, it's the opposite is true. The reason is because water is bent, and when it forms a crystal, it forms a hexagonal structure with a lot of empty spaces. I can show you a picture of that later, but that is the reason why ice is less dense. Gypsum, for this one, I just looked at the passage where they talked about gypsum over here, calcium sulfate. I know that the sulfate ion has a charge of 2 minus, and I know calcium, when it turns into its cation, has a charge of 2 plus. So you just need 1 calcium and 1 sulfate. This one, so I'm going to have to talk to you a little bit more about what happens with radiation, or rather radioactive decay. So, they're saying product of the decay of iodine 131. So over here, iodine 131 undergoes beta minus decay. Beta minus is the same thing as an electron. If it was beta positive, it would be a positron. Positron and electron are exactly the same in that they don't really have mass, or rather they have negligible mass, but a positron is positively charged and an electron is negatively charged. So the beta minus decay is the electron over here. And then gamma emission. Gamma is like the most dangerous type of radiation. And that type of dangerous type of radiation we call ionizing radiation because it causes, things to ionize. And so that leaves us with A and B. So how do we know if it's xenon 131 or tellurium, I think, 131? So if I look at the periodic table, right? So we have iodine, right? And it loses an electron. Okay? So does it go to the right to make the xenon 131 or left to make the tellurium 131? It's still going to be 131 because, it's losing an electron, which doesn't have mass. And a gamma ray is just a photon, doesn't have mass either. So we're basically looking at something that we can add an electron to that would form the iodine. So, or vice versa, when iodine loses an electron, what would its electron configuration be, basically? So if it loses an electron, it means that on the left-hand side, it'll be iodine 131. On the right-hand side, it'll be an electron plus the thing that it turns into. They're both equal on both sides. So basically, the answer is going to be xenon because xenon plus an electron is equal to iodine. Anyway, I'll have to go into that more in depth later. Here, why do researchers choose to study pediatric rather than adult thyroid cancer cases? So basically, I don't know if it tells you this. Well, I guess. Okay, so basically all we know is that we know the amounts of I-131 that is in these regions, right? And it's just that children, if they get the same dose of I-31, it's just higher compared to an adult. Because basically children weigh less. This one, I guess I went through it fast, but they're basically saying, is it safe for people in area 4 and 5 that have low and minimal amounts of I-31 to not have any increased risk of developing thyroid cancer? And if you look at these, they're pretty much all around 2,000 compared to moderate, where between 2013 and 2014 it doubles, and high and highest where it doubles from 2012 to 2013 to 2014. It doubles or more than doubles each time. So are the people who are here in these regions right in saying that their children have no increased risk of developing thyroid cancer? So I chose wrong here. It's plausible, but we want something to be always correct, right? And we basically can't say something that they have no increased risk of thyroid cancer, because that's just too extreme of a statement. It could be that it takes more than 3 years. This is just 2012, 2013, and 2014. So it could take longer, basically. And also, the gamma radiation from this could just kill the cells first. So maybe, after a while, you'll be able to see cancer come up. More on that later. 9, let's see. Okay, yeah, small to moderate doses are more likely to cause thyroid cancer than extremely large doses. Why? So it's basically just that small doses don't have, because remember, it releases ionized, the gamma radiation that basically just kills the cells. So, that'll kill cancer cells as well. So basically, like if it's too high, all that gamma radiation is going to kill the cells. Which, if you kill the cells are dead. They're not there anymore, so they're not going to be able to, become cancerous. But the low amounts or small amounts of I-131 will not have enough gamma radiation to kill those cells. The cells will be alive, but there'll be enough radiation to damage the DNA of the cell, causing them to become cancerous. Okay, this one. Which ones are chiral? So chiral just mean, first of all, in order for something to be chiral, it has to be like an atom where that's attached to, at least in terms of it's going to be carbon most of the time. Carbon can have bonds to 4 other atoms, and all 4 of those atoms must be different. So, it's really just this one over here, because its carbon is bonded to CH3, and then a C double bonded, like a carbonyl group over here, an H over here, and then like a CH2 over here. So they're all different, so it's just that's the only one that's chiral. Everything else is bonded to some similar things. Not similar things, some identical things. How do you separate this from this? They're basically the same thing, except the Al means that it's an aldehyde, and then this is just an acid portion of it. So I chose extraction based on their differing solubilities, because I know that the carboxylic acid group has more, can hydrogen bond with whatever, with water molecules, so it's going to be more soluble than just the aldehyde itself. So that's how you can change it. Alright, what do boiling chips and vacuum distillation do? Boiling chips just basically give the liquid a place to start forming bubbles, so it can boil effectively, to prevent superheating, which means that the water gets too hot. Instead of boiling, it just gets hotter and hotter and hotter. And vacuum distillation, what that does, so it's just like a regular distillation process, so like this, but this is attached to a vacuum, and what that does is it lowers the vapor pressure, it basically lowers the vapor pressure, and so boiling again happens when the vapor pressure is equal to the atmospheric pressure. But if you introduce a vacuum here, you're basically reducing the atmospheric pressure. Like for instance, like if there was something like liquid here, anything above that would be like vapor pressure, and if this was just connected to the outside, it would be atmospheric pressure pushing down on it. I can talk about this more next time. The vacuum just takes out the atmospheric pressure, so it's lowered, and yeah, the boiling point would just be lower, basically. Let's see, this one. So the liquid remaining in the round bottom flask, which one is it going to be? So it's basically the liquid that took longer to evaporate or to boil. And so which one would take longer to boil? It's going to be the thing that is more soluble in water, which we already determined was the acid version of this molecule. Alright, formal charges. So basically, the way I do this is just count the number of valence electrons it has, or rather supposed to have, and subtract it by the number of whatever valence electrons that it has in whatever molecule they give us. So oxygen's supposed to have 6, but it has here 1, 2, 3, 4, 5. So 6 minus 5 is 1, so that's going to be 1, positive 1. Nitrogen has 5 valence electrons. It has over here 1, 2, 3, 4. 5 minus 4, 1. So 2, it's going to be 1 over here. Here, so oxygen, again, is supposed to have 6 valence electrons. It has 1, 2, 3, 4, 5, 6, 7. So 6 minus 7 is negative 1. So it's going to be A. This one we already did, basically. You don't have to use this thing. You know the shortcut, the radical 2GH. So that's just radical 400, which is just 20. So that's that. This one, we're looking at stereocenters, aka, you know, chiral centers, same thing. So there's one here, one here, one here, 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 and here. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 of them, okay? This one, I got this right. Okay, so preferred ion configuration of elements on the periodic table. So they want to be like the noble gases, right? So A and C both basically say that. But A says same core electron configuration as a noble gas. C says same valence electron configuration. You want it to be the valence electron configuration because the core electron stuff is just that doesn't really matter, really. It's about the valence electrons. That's a bad explanation. I'll do a better one next time I see you. Okay, this one I kind of talked about. You see how it's torque, right? So they just did 13 divided by 98, which again, like, you know, they're pretending like you can just do that, which, you know, you can't. So I would just do the thing where I did 13 divided by 100, which gives me, you know, 0.13. And then I would notice that 98 is less than 100, so it's a smaller denominator, so our answer should be greater than 0.13. And this is the only one that's greater than 0.13. It's not greater by that much. This one we did also. We just did 5.7 divided by, you know, 0.2, which is 1 over 5. So 5.7 divide or multiplied by 5. So they just rounded it to 6. But of course I showed you how to do that, you know, more precisely. Oh yeah, this one, you asked me how I knew it was 750. So I knew that it was going to be basically a resultant between, you know, basically like the weight. So I guess I could show you here. The weight of the person is 650 and the turning is going to be 90 degrees from that. So that's going to be, I guess, 65 times 5, which is just, I guess, 650 divided by 2, which is 325. And then the resultant of that. And so they did the Pythagorean theorem, but I also know that the resultant is going to be greater than the difference between the two sides, like, you know, of like a triangle, right triangle. And it's going to be less than the sum of the two sides. So I know that 650 is one of them, 325 is another, If I subtract them, like, it's just going to be 325, so it has to be greater than that. And if I add them, I get basically like 975. So it has to be less than that. And 750 is the only one that's in between. Oh, and it said brutal, but it definitely isn't that hard. This one, like, I didn't really want to read this, so I guess I did this really fast. But I think, whatever, I'll come back to that. This one, whatever, come back to. This one, oh yeah, we did this before. Basically just, yeah, we did this before, okay. This one, I mean, we know that they said that it is a competitive, yeah. Where is that? They said it's a competitive inhibitor. So what happens with that? Vmax unchanged, KM increases. Here, I guess I did this fast, but they're asking what happens when it's to maximize its inhibition of ACE. So ACE maximized in this region over here, and here 3.8, between 3.8 and 9.5, and the pKa of this, oh, it's 3.7. That's why I got it wrong, because, well, it'll be in between these. So basically this should be, okay, so 3.8 to 9.5. So that means if this is pKa is 3.7, at 3.8 it will be deprotonated, because it's going to be in an environment that's more basic than, like 3.8 is more basic than 3.7. And this 9.5, so 9.8 is more basic than, 9.8, yeah, it's more basic than 9.5, but we're picking, between this range here, so this is going to stay protonated. I'll explain that better next time. This one, I didn't really want to do the math, but I just basically looked at the fact that it's dissolved in 3 liters of plasma, and at pH 7.4, which will be like around here, and so I know that these are micromolars, so I'm just going to choose the one with a microgram. This is just, wow, they really said this is tough. So this is just basically Newton's third law. Like, if a book experienced a gravitational force due to the Earth, third law states that the Earth experiences a gravitational force in the opposite direction, but equivalent amount, from the book. That's it right there. This one, so nitrogen N2, it's like the most like abundant gas in the atmosphere, and it's just, N2, it's basically inert. It doesn't do anything. It doesn't react with anything or anything like that. And in the laboratory, like, they can use that to just provide something in the atmosphere that isn't oxygen, which reacts to things. So yeah, N2 is that. Acetone, I know it's a ketone, which means it has, a carbonyl group, C double bonded to an O, and that's going to be planar, and it's going to be bonded to 2 other things, so it's 120 degrees. This we went over. This, okay, so retinol synthesis, talking about, you know, the final step here. So NADH, E2, so that's a dehydrogenase, right? And so I mean, dehydrogenase you can memorize as being something that causes reduction, but what I looked at was just how it went from aldehyde to alcohol, and you know that's in the direction of reduction. Um, so I'm gonna pick something that reduces things. So that means not gonna oxidize, because like ozone here and KMNO4 will cause oxidation. Jeez. But this and this cause hydration. This just causes hydration too far. It'll take it all the way back to an alkane. And by the way, like if you oxidize an alkane, it'll go like alkane, alkene, alcohol, and then aldehyde or ketone, and then carboxylic acid, and then ultimately carbon dioxide. And then for reduction, it's going to go backwards. So yeah, we're left with this and this, but this is just much, much stronger. 32 here. Terpenes are basically the building blocks of cholesterol. So we're going to look for things that are from cholesterol. So it's going to be estrogen and aldosterone. And you know that aldosterone is one because ster is in that word. And then, you know, that's what they look like. Enzyme 1, E1, they said it's beta-carotene, blah, 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 monooxygenase. And I just know that that's a oxidoreductase, because they're named like that. Conversion of retinal to retinol. So, like, you should know that this IR peak, basically, it's like the one they ask most of the time. Just the carbonyl group is always going to be like at 1700 to 1750, and that's lost when you turned it into, you know, an alcohol. So it's going to be a disappearance there. Here they're just asking what would make disulfide bonds, and you should know that cysteine, like that's cysteine. Two cysteines form a disulfide bond. Like they basically remove the H's and they bond together like that. Chiral center for beta ODAP. Beta ODAP they show right here. So this is gone because it's not even the right molecule. And then yeah, chiral center. Remember something that's bonded to, you know, 4 different things or whatever. So it can't be this. And it's not going to be this because this has 2 hydrogens that are identical. So it's going to be that one. This one, so I was able to look at this pretty fast. So I know here that it says whole eggs each contain 400 milligrams of methionine per 100 grams of weight. Now, if they said that they're given 5 eggs containing 50 grams, that are 50 grams each, and if 400 milligrams of methionine are in 100 grams, that means that in 50 grams of, you know, an egg, it'll be 200 milligrams of methionine. And if they got 5 of those, 200 times 5 is basically 1,000. So, and this is the only one that's 1,000 right here. Here, talking about figure 2. So again, I looked at this pretty quickly, but I was able to see that that they were supposed to fast for 12 hours. So like whatever, they were given these seeds here at whatever time equals 10, I think, or 0, something like that. But then they were supposed to fast before, but after 10 hours they were given a meal, so that's where they were given a meal. that's supposed to have some, sulfur content or methionine content, but you don't really see it jump up too much, like the methionine content. So sulfur-rich meal, the sulfur-rich meal again is, the eggs and stuff, demonstrated no significant effect compared to baseline, right? So, it doesn't really, like, this is baseline over here. It's like barely any difference, especially because if you remember that the error bars overlap. All right, this one, why didn't they do this with volunteers with sulfur deficient diets? So they're basically looking at population sulfur deficient diets, and they're predisposed to neurological degradation after eating L. sativus leaves or seeds. So they brought in people whose diets were rich in sulfur, right? Now, if they gave these seeds to people who had sulfur deficient diets, they're going to get neurological degradation. So, the reason that they're not going to do that is because the health risks of giving these seeds to sulfur deficient patients are too high. They're going to get, brain neurological degradation. All right, this one I didn't really want to do, so whatever, I'll come back. Okay, and this is kind of like an easy kind of one, like, basically, like, everything in our body, all the chemical reactions in our body are supposed to happen really slowly. The reason that they don't is because they have a catalyst, aka enzyme. And an enzyme, so enzyme doesn't really do anything thermodynamically speaking. It only does something kinetically speaking by reducing the activation energy. So it's going to be D. This one, so again, I did this pretty fast, but like I just looked at here for, so they're asking what basically happens for formation of fructose 6-phosphate from glucose and ATP. So I know that step 1 of glycolysis is -4 kilocals, aka -4,000, right? And then it's coupled to the formation of fructose 6-phosphate, and that's positive 400. So I'm just going to add these. So -4,000 plus 400 is going to be like -3,600, or -3.6 kilocals. So I chose that. There's 2 of them. KEQ for the reaction, greater than 1, less than 1. KEQ, is going to be just products over reactants. And since it's exergonic, right? Like, it's moving forward, it's going to produce more products than reactants. So KEQ is going to be greater than 1. This one, yeah, I just didn't really want to read it, so I guess I'll come back to that. This one, okay, so you should know that basically angle of incidence is always equal to angle of reflection. So 1, Roman numeral 1 is true. They're asking which ones are not true. Angle of refraction will not be equal. Angle of refraction is basically 90 degrees minus angle of incidence. So basically 60. So angle of refraction is 30 degrees is incorrect. Total internal reflection will result depending on the critical angle. So total internal reflection is something that happens at a critical angle, but it's for something that's inside of the same medium. I can talk more about that later. But yeah, both of these won't happen. Here, so XeF4, it's basically it's a octahedral, I believe. I believe it's an octahedral molecule. So I'll go over like geometry with you, like for molecules. And then NH3 is basically a trigonal pyramidal, and sp3d2, sp3. I'll go over that stuff with you. This one seems sorry. So this one was a lot of stuff to read, which obviously I don't like to do. All I looked at was which solvent would be least favorable for CFOS and C-June. Then I look over here, and I see that C-June and CFOS are soluble in the cytosol or nucleus, aka water soluble. So water is polar, so water won't be it. Ethanol is polar, won't be it. Phosphate buffered saline is, a salt water kind of concentration solution with phosphate, which is basically a negative ion, basically polar and stuff. Hexane is the only thing that's nonpolar, so it won't be soluble in that. This one, so I know that you looked at it like, it's the only number here, but I just want to tell you that, it's an association constant for EGFR, and, we see over here EGFR plus EGF, they associate to get to, this is the binding of it, EGFR, EGF. And so the association constant is 5.61 times 10 to the 6th. And KEQ is just this, right, over this times that, like in terms of concentrations. And there's nothing else here, so it's just going to be the same thing here. This one, I guess I went pretty fast on these because I didn't really want to make sense of this table. But this one I guess you could answer without the table, because we're just looking at, I guess I could talk to you about like electron withdrawing groups, electron donating groups, but this one they just really looked at the table. So I guess they looked at this, X to X positive, whatever. I'll come back to that. This one, I think I just looked at, I looked at, like, just, like, in order of, like, figuring out, like, which one of these to use, I think I used this. Yeah, I used RSE. So this is the most negative one, NO2. Then it's this, so that, then this, then that, and that. Whatever. This one, what did I do here? Oh, if the reaction became hot, it means that it is exothermic. So I looked at this over here, and it's H is enthalpy, right? So heat energy. So all these are exothermic except for NO2. So, and it says except, so that's the one, NO2 one. This one, so, yeah, actually it will be destabilizing because it's very electronegative. Again, I'll go over the electron withdrawing groups and stuff later. This one, yeah, I just didn't want to deal with it, so I just went through it fast. Here, so right away, again, units help. Pascal is a unit of pressure. Pressure is force over area. So aka like newtons over square meters. And if it's, pressure divided by meters, then it'll be newtons over square meters times 1 over meters. So that'll just give me newtons over cubic meters. That's not, they're asking for lift force. Force is always in newtons. So these two are out. Now we're just looking for these two because these are in piconewtons. And I mean, I guess I just was like, what would be the last to detach from the vascular wall? Something that requires a greatest lift force, which is this. So that's, you know, the answer I chose. You can also see it over here. Lift force is in, you know, this piconewtons over here. Relationship between lift force and the vesicle radius. So I looked at this. So they basically said that the lift force is equal to the apparent weight, so P. And then, you know, radius is capital R. So basically lift force, or P, is proportional to the cube of the radius. This is an exponential, you know, relationship. ITO coated plate. So basically over here they're talking about, you know, 2 glass plates. That pretty much just tells you that it's, you know, it's a capacitor. It's coated with transparent indium tin oxide, ITO. So basically, what are these plates functioning as? Capacitor. Then here, what did I do? Oh, 2 and 3. Okay. So first of all, what describes it? Opaque? No. I mean, it tells you right here that it's transparent. So it's not going to be opaque. So anything with 1 is out. Then electrically conducting, so that's true because it, you know, it's on the conductive faces of the, you know, capacitor plates. And I guess I just saw solutions, so I didn't really think about whether it's going to be solid or not. I think concentrations are altered to cause density variations. That could have something to do with it. Anyway, I'll look into that better next time. This, alright, I went through this fast, but I'll go, like, as in, I just, like, picked an answer. I didn't really do it. So I'll do this one, because it's a math one. I don't think it'll be that bad. This one, yeah, so this is a dry heat. I mean, like, you know, humidity is a major, you know, part of so I mean, like, it's not just if some place is hot, like, you know, you're gonna sweat, right? But if the humidity is high, then there's too much water vapor in the air, and so your sweat isn't going to evaporate. So you're just gonna feel, you know, you're gonna feel like crap. So dry heat it means that, you know, there isn't that much humidity, so your sweat will evaporate faster and you'll feel more cool. This one, tubulin. I guess I knew that electron transport didn't have anything to do with microtubules and stuff. Mitosis and meiosis definitely do. And I guess I forgot that transport also does, because it's overall cytoskeleton, right? So that's that. And, oh, I guess we're done. So, there.